Alright, welcome back, and today I'm sorry, but the audio quality is going to be worse than normal. So last time we talked about the addition of matrices, subtraction, of course, scalar multiplication, as well as matrix multiplication, and lastly, identity matrices. So now I'm going to introduce something called a scalar matrix, or a kth order identity matrix, where k is a scalar. So, like I said, kth order identity matrix. For example, a third order identity matrix looks something like this. This does the same if you take this, which is the same as 3i, right? Scalar multiplication. If you take 3i, multiply it by some other matrix, it's the same as taking 3 multiplied by the matrix. So essentially, well, this operation is scalar is matrix multiplication because the 3i is a matrix, and this is scalar multiplication. So it's two different kind of operations, but it gives you the same thing. And also later on, adding a scalar matrix of this sort to another matrix, it shifts the eigenvalues by whatever the scalar is. Okay. So now let's talk about taking the transpose of a matrix. So the transpose, denoted A to the T, is the matrix obtained when you write the columns of A in the same order as rows. So for example, if you have this 2 by 3 matrix, 1, 2, 3, 4, 5, 6, you take the transpose, you get 1, 2, 3, 4, 5, 6. Okay, so essentially you flip it on the side, but kind of not really, because, well, yeah, but just remember this is the order you should have. The first row becomes the first column, and the second row becomes the second column, and so on and so forth if you have larger matrices. If you have some row vector like this, the transpose turns it into a column vector. So if A is an m by n matrix, B would be an n times m matrix if B is equal to the transpose. There are some properties of the transpose. If A and B are matrices and K is a scalar, when the sum and product are defined, you have 4 properties. So firstly, taking the transpose of the sum is the same as adding up the respective transposes. Second property, if you take the transpose of the matrix, you get your matrix back. This should be obvious. If you have a scalar multiplied by a matrix and you take the transpose, it is the same as multiplying that scalar by the transpose of the matrix. This is also obvious. So this one is going to be important. It says that the transpose of a product is equal to the product of the transposes, but in a reverse order. So note, for here we have AB, and now it's B transpose A transpose. So that's important. And this is the product of the 2 respective transposes. So you should remember this. I'm gonna box it in red. Now let's move on to talking about the trace and diagonal. So these are closely related. You'll see really soon. So if you have a matrix A, remember we talked about you can write the elements in this form. The diagonal consists, or the min diagonal consists of the elements with the same subscripts. So for a 2 by 2 matrix, we want these 2 values. First row, first column, second row, second column. Okay, the trace of A, written TR bracket A, is given by adding up the diagonal values, well, however many you have, right? Depends on how big your matrix is. Again, we have some properties. Firstly, the same sum property, taking the trace of 2 matrices is the same as summing up the respective traces. The second one is that taking the trace of the result of a scalar multiplication is the same as taking the scalar and multiplying it by the trace. Should also make sense because, well, the scalar simply acts on the elements one by one, same way. for each element, so it's going to be the same. Third one is that the trace of a transposed matrix is the same as the trace. But this is only true for square matrices, of course, because to have a diagonal, you need to be a square matrix. So for a trace to be defined, you need to have a square matrix. So that's something I forgot to talk about. And lastly, the trace of the product of two matrices is the same as the reverse product. So this is strange, right? Normally, AB is not equal to BA. Well, in most cases, generally, but the trace is actually the same. Let's take some concrete examples. So if you have some matrix A, it looks like this. 1, 2, 3, minus 4, minus 4, minus 4. Yeah, sure. 5, 6, 7. And B, it looks like this. 2, minus 5, 1, 0, 3, minus 2, 1, 2, minus 4. If you have two matrices that look like this, first I want you to write down diagonal, like such. 1, minus 4. Just identify it really quickly for the second matrix. 2, 3, minus 4. Now let's take the traces. Trace of A is 1 minus 4 plus 7, which is equal to 4. Trace of B is 2 plus 3 minus 4, which is equal to 1. And you can check the properties that we have if you feel like it. We'll do it quickly. The trace of A plus B, well, A plus B, your new will have 1 plus 2, 3, minus 4 plus 3 minus 1, and 3. So it will be equal to 3 minus 1 plus 3, which is equal to 5. And then if you check the trace of A plus the trace of B, we'll get 4 plus 1, which is 5, and these two are the same. You can do this for the rest of the properties if you feel like it. And that will be it for today. And thank you for watching as always, and I'll be back soon.